Today topic is engineering stress and strain curve. What is mean by engineering stress and strain curve? The definitions: it is a graph plotted between stress and strain when a material is subjected to tensile test. It is shown how a material behaves under load until it fractures. This is a definition for engineering stress and strain curve. All of note that this is definitions. And next, the C for graph. First one is elastic region or elastic deformation. What is elastic deformations? Initial strength line portion of the curve. When the load is removed, the material returns to the original shape. This is an elastic deformation. The second one is Young's models. What is mean by Young's models? The slope of the straight line part of the curve indicates stiffness of the material. Formula: Young's modulus equal to stress divided by strain. This is definition for the Young's modulus. The third point is yield point where plastic deformations begins. Behind the point, the materials will not return to the original shape after undercooling. This is a yield point. Fourth one is plastic region the after the yield point. This is for plastic region. Fifth one is uniform plastic deformations. Deformations occur uniformly along the length of the specimen. This is definition for uniform plastic region. The sixth one is non-uniform plastic region. Deform becomes localized region. This is for non-uniform plastic region. The seventh one is ultimate tensile test, UTS. The mean maximum stress the material can withstand highest point of the curve. The eighth one is necking. What is mean by necking of the curve? The reduction is cross-sectional area at region of the specific specimen occur after UTS, ultimate tensile strength. This is a meaning for necking. The ninth one is fracture point, the last of the point, the final point where the materials breaks completely. The final point where the materials breaks completely. This mean for fractional point. The another slide is engineering stress strain curve. Basic design information of the strength of the materials, the first point, and acceptance tense of the specific of the materials is the second point. This is other one is average longitudinal tensile stress. The formula S equal to P divided by A naught. The another one is average linear strain, E equal to L minus L naught divided by L naught. This is formula for average linear strain. The third slide, the factor affecting shape and magnitude of stress strain curve. The composition, heat treatment, periodicity of plastic deformation. This is one of the metallurgical factors. Strain rate, temperature, rate of stress. This is one of the stress conditions. Another slide, recoverable elastic strain and plastic strain. Difference between the recoverable elastic strain and plastic strain. Recoverable strain is the temperature deformation that disappears upon unloading. The plastic strain is the permanent deformation remaining after the load is removed. For differentiation for the recoverable elastic strain and plastic strain, the loading of tensile sample begin yield point to A and the unloading give the unloading curve AA with its slope parallel to elastic Young's modulus. All of you see this is graph. Recoverable elastic strain B on unloading is given by B equal to P1 divided by A naught divided by E. The The permanent plastic stain, it is A. The loading and unloading following OABB gives plastic deformation C. Wearless elastic deformation under unloading is D. The another slide. The tensile strength. The tensile strength or ultimate tensile strength UTS. The ultimate tensile strength. SU is the maximum load. P max divided by the original cross sectional area. A naught of the specimen. SU equal to P max divided by A naught. This is the tensile strength of the formula. The tensile strength is the most value quoted of the tensile stress result. The useful for specifications, quality control, a product. The engineering designs safety factors should be applied. This is for tensile stress applications. What is yielding? The next slide is yielding. The what is yielding? The transition point where a materials cross to the behave elastically and to deform permanently under stress. This is a yielding. This list of the data. The first one is true elastic limit, proportional limit, elastic limit, yield strength. First one is true elastic limit. Based on microstructure measurement, a strain on 2 order of the 2 in 10 power 6 very low value and is related to the motion of few hundred dislocations. The second one is proportional limit. The highest stress at which stress is directly proportional to strain. Third one is elastic limit. In the greater stress the material can withstand without any measurable permanent strain after unloading. Elastic limit, proportional limit. Elastic limit less than equal to proportional limit. Fourth one is yield strength. Is the strength required to produce a small specific amount of deformation. The next slide. Yield strength of material. Yield strength of material is the definitions. What is definitions? The critical strength level at which a crosses to deform elastically and it begins to deform plastically, meaning it will not return to its original shape. It is a form meant by yield strength of material. At another point, FCC lattice material have no definite yield point. The yield strength is therefore defined by the opposite of yielding. Yielding strength can be improved by work hardening up to 300:1 stronger than original. Alloying of the AL can improve elastic limit 1.5 to 2 times. All of you know this is graph. Improvement of yielding by cold working. Improvement is elastic limit by alloying. The two types of graphs are drawing. The next slide. The ductility. Ductility is qualitative subject property of material. It is general ductility of the interested. There are different ways. The ductility used for industries for different ways. First one is for metal working operation. Second one is for stress calculation of the productions of severe load. Third one is for indication of any changes, heat treatment or processing conditional of in metal. First one is for metal working operation. Indicating amount of deformation can be applied without failure. For the second one is for stress calculation of the production of severe load, indicating the ability for metal to follow plastically before failure. Third one is for indication of the any changes, heat treatment or processing condition in metal. The next slide. Measures of ductility. Elongation. The elongation formula E of x E of f equal to L of f minus L naught divided by L naught. Reduction of area Q equal to A naught minus AF divided by A naught. This is formula for reduction of area Q. E of LF minus L naught divided by L naught equal to, this is formula for elongations. These parameters are obtained after fracture by putting specimen back together and taking the measurement. Zero gauge length of elongations E naught equal to Q divided by 1 minus Q. This is the zero gauge length of the elongations. The next slide. Modulus of velocity. Modulus of velocity or Young's modulus is measure of materials stiffness. Modulus of velocity is determined by the binding force between the atoms. Cannot change E but can improve by forming compositions. Only slightly after the alloying additions, the heat treatment of cold work. The Young's modulus. The definitions is already for readings. The Young's modulus definitions. Slope of the straight line part of the curve indicating stiffness of the materials. The formula Young's modulus equal to stress divided by strain. This is the Young's modulus formula. The resilience. Resilience is the ability of materials to absorb the energy when elastically deformed and to return it is unloaded. Usually measurement by modulus of resilience. Unit resilience. Yes, the brackets closed bracket. Strain energy per unit volume required to stress the material from 0 to the L stress. Sigma naught. All of you note this graph for modulus of reliance UR. The UR formula is UR equal to 1 divided by 2, 1 by 2 S naught E naught. This is formula for modulus of reliances. This another one is U naught equal to 1 divided by 2 sigma naught in x equal to UR equal to 1 divided by 2 S naught E naught equal to S square naught divided by 2E. The another slide. The next one is note. The last point, the note of the reliance. For mechanical springs, high yield stress and low modulus of velocity. This is important one of the resilience. All of the note. This is note. The another slide. Toughness. Toughness is an ability to absorb energy in the plastic range, or the ability to withstand since L stresses above the L stresses without fracture. Can be simply defined by the area under the stress strain curve. The structural stress all that have a lower yield point but more ductility than high carbon spring steel. Structure steel is therefore structure. Toughness equal to stress plus ductility. UT approximately SUEF. UT approximately S naught plus SU divided by 2F. This formula for ductility material. UT approximately 2 divided by 3 SUEF. This formula for brittle material. Thank you all. Thank you for these opportunities.